Theories for metal ligands bonding in complex. There are three theories to explain the nature of bonding in transition metal complex. First, valence bond theory (VBT). Second, crystal field theory (CFT). Third, ligand field theory (LFT) or molecular orbital theory (MO2) or address crystal field theory (ACFT). First, valence bond theory. This theory developed mainly by Pauling. This theory is based on the following assumption. First, centrometer cation or atom, as a case may be, make available a number of vacant sp or the orbital equal to its coordination number to form coordinate covalent bond with orbital on the ligands. Second, since the maximum angular overlaps of two orbitals form the strongest bond, therefore these weakened atomic orbitals of metals are hybridized to form a new set of equivalent bonding orbitals called hybrid orbital. These orbitals have same geometry and same energy. These orbitals also have definite directional properties, that is, this orbital point in the direction of ligands. The geometry and hybridization are related to one another. Once you know the geometry of a complex compound, you automatically know which orbital of the metal cation or atom use the relation between the geometry of the complex and hybridization in given in table 4.1. Bonding in metal complex arises when a field ligand orbital containing a lone pair of electrons overlap a vacant hybrid orbitals on metal cations or atom to form a coordinate covalent bond. Vacant metal hybrid orbitals overlap with ligand orbital containing a pair of ligand to form metal covalent bond, where metal and ligand, both the orbital, are overlap to form a hybrid orbital. The magnetic moment, that is the number of unpaired electron, and the coordination number of metal cation or atom, decide the hybridizations and geometry of the complex. Therefore, the magnetic moment, coordination number, and hybridization and geometry are related to one another. The knowledge of magnetic moment can be of great help in ascertaining the nature of ligand and type of complex. Each ligand has at least one orbital containing a lone pair of electrons. Pauling classified the ligands into two categories, that is, one strong electron donating ligand or simply strong ligand like Cn- Cu, etc. Two weak ligands or highly electronegative ligand like fluoride, chloride, oxygen containing ligands, etc. Sixth, strong ligands have tendency to pair up the d electron of the metal cation or atom to provide the necessary orbital for hybridization, but the pairing of electrons does not violate the Hund's rule of maximum multiplicity. On the other hand, weak ligands do not have the tendency to pair up the d electron. That is, in presence of weak ligand, electronic configuration of the d electron is seen as in free metal cations or atoms. 7. Bond formed between metal and strong ligand such as Cn- and Cu is considered to be covalent. On the other hand, the bond formed between the metal and weak or highly electronegative ligand like fluoride minus is not covalent, but it is ionic. The bond formed between metal and strong ligands like Cn-, carbon monoxide, etc. is considered to be covalent. This would require in many cases the pairing of d electron to provide the necessary orbital for hybridization. Ninth, in octahedral complex, the central metal cation is either D2sp3 or sp3d2 hybridized. The d orbital involved in D2sp3 hybridization belong to the inner shell, that is n-1 d orbital, and this complex are called as inner orbital complex. In case of sp3d2 hybridization, the d orbital belong to the outermost shell, that is n-d orbital, and the complex are called outer orbital complex. The octahedral complex involved with D2sp3 hybridization are more stable than those of sp3d2. The d orbital involved in hybridization of octahedral complex are dx2y2 and dz2. In tetrahedral complex, the metal cation or atom is either sp3 or sp or sd3 hybridization. sp3 hybridized. The d orbital involved in sd3 hybridization are dxy, dyz, and dzx. In square planar complex, the metal cation is dsp2 hybridized. The p and the orbital involved in dsp2 hybridization are px, py, and dx2y2, leaving pz and dz2 orbital projecting above and below the plane of the complex. 10th, in case of second and third series transition metal complex, the d orbital involved in hybridization are n orbital, that is n-1 d orbital, because the outer d orbital, that is n d orbital, become too diffuse to bond well. For 11, the complex having one or more unpaired electron are paramagnetic, and the complex having only paired electron are diamagnetic. 4.1, hybrid orbital for common coordination geometry. Coordination number 2, hybridization. sp orbital involve s and px. Bond angle is 180 degree. Geometry is linear. Example as Ag and S3 2 plus. Coordination number 3, hybridization is sp2 orbital involved is s, px, and py. Bond angle is 120 degree. Triangular planar. Example is AgI3 minus. Coordination number 5, hybridization is sp3. Orbital which is involved is s, px, py, and pz. 109 degree 28 minute tetrahedral. Example is COCl4 2 minus NiCl4 2 minus. Coordination number is 4. Hybridization is sd3. Bond involved is f, dxy, dyz, dzx. Bond angles 109 degree 28 minute. Geometry is tetrahedral. Example is MnO4 minus Cr2O7 2 minus Cr4 2 minus. Coordination number 4, hybridization is dsp2 or sp2d. Hybrid or orbital involved is s, px, py, dxy2, s, px, py, dx2y2, dy2. Um, Bond angle is 90 degree. Geometry is square planar. NiCN4 2 minus dsp2, CuNS3 4 2 minus sp2d. Coordination number 5, dsp3 or bond orbital involved is s, px, py, pz, dz2. Bond angle is 90 degree, 120 degree. Geometry is trigonal bipyramidal. FeCO5. Coordination number 5, dsp3. Bond involved is orbital involved is s, px, py, pz, and dx2y2. Bond angle is 90 degree, 90 degree square pyramidal. Example is NiCN4 CN5 3 minus. Then coordination number is 6, d2 sp3. Orbital involved is d4s, 4px, 4py, 4pz, 3d x2y2, 3d dz2, 90 degree, 90 degree bond angle. Geometry is inner orbital octahedral. Example is CrH2O6 3 plus FeCN6 4 minus. Coordination number 6, sp3 d2 4s, 4px, 4py, 4pz, 4dx2y2, and 4dz2. Bond angle is 90 degree, 90 degree. Geometry is outer orbital octahedral. COH2O6 2 plus, COFe6 4 minus. Now let us discuss the valence bond theory for octahedral, tetrahedral, and square planar complex, taking some example. Octahedral complex, A inner orbital complex. Let us discuss inner orbital complex, taking some example. COCN6 3 minus ion. In this complex, oxidation state of cobalt is +3. The valence shell electronic configuration of CO3 plus is 3d6. Magnetic measurement indicate that COCN6 3 minus is diamagnetic. All 6 3d electrons are therefore paired and occupy 3 of 5 3d orbitals, and Cn minus ligands are strong and therefore causes pairing of 3d electron. The vacant 2 3d orbital combine with the vacant 4s and 4p orbital to form 6d2 sp3 hybrid orbital. These 6 hybrid orbital overlap with 6 field orbital of ligand, one on each of the ligand, and thus 6 coordinate covalent bond are formed. Cobalt atom, atomic number is 27. 3d 7 1 2 3 4 5 6 7 7 electrons present. 4s having 2 electron, 4p is empty. After losing 3 electron by cobalt will form into CO3 plus ion. Now in 3D, 6 electron will be there instead of 7, and 4s orbital will be empty, and 4p orbital is usually empty. This orbital 4s 4p will hybridize COC6 3 minus ion. The 6 cyanide had share the electron to form D2sp3 hybridizations. Cyanide is a strong field ligand. D2sp3 hybridization octahedral geometry in an orbital complex. CONO264 minus. In this complex ion, oxidation state of cobalt is +2 and its valence shell is electronic configuration is 3d7. Magnetic moment measurement indicate that this complex ion is paramagnetic corresponding to presence of one unpaired electron. The NO2 minus ligand are strong. They therefore cause pairing of metal 3d electron. Pauling suggests that the two vacant 3d orbitals are made available by promotion of an unpaired electron from a 3d orbital to 5s orbital so that CO2 plus ion get D2sp3 hybridized. The presence of an unpaired electron in 5s orbital is supported by the fact that 5s orbital has very high energy and the electron present in it is loosely bound and can be removed easily. Experimentally, it is also observed that CONO264 minus oxidized by air or H2O2 easily to give CONO263 minus. This indicates that complex CONO264 minus is unstable in air. Thus, this complex should be prepared in inert atmosphere. Cobalt atom Z atomic number is 27, 3d7, 4s2, 4p is empty, 5 is also empty. After losing 2 electrons, cobalt atom is changed into CO2 plus ion. So, in 3D, 7 electron will be present, 4s will be empty, 4p and 5s obviously will be empty. So, CONO264 minus, okay, will share 12 electrons. One unpaired electron is present after D2sp3 hybridizations. So D2sp3 hybridization octahedral geometry in a orbital complex will show paramagnetic due to presence of unpaired electron. NO is a strong field ligand. Next is manganese MnCN63 minus. In this complex ion, oxidation state of Mn is +3 and its valence shell electronic configuration is 3d4. Magnetic measurements show that this complex ion is paramagnetic corresponding to unpaired electron. All 4 electrons occupy just 3 of the 5 3d orbitals, leaving 2 3d orbitals vacant. These 2 vacant 3d orbitals combine with the vacant 4s and 4p orbital to give 6 D2sp3 hybrid orbital. This hybrid orbital form bond with ligand by accepting 6 pair of electrons, 1 pair from each of the 6 ligand. 6 Since Cn minus is a strong ligand and has a tendency to pair up the d electron on metal, but it causes pairing of 2 electrons, only leaving 2 electrons as unpaired. If all electrons become paired, then it will violate the Hund's rule of maximum multiplicity. Manganese atomic number 25, 3d, 5, 4s, 2, 4p is empty. After losing 3 electrons, Mn manganese atom change into Mn3 plus. So in 3d orbital, 4 electron is present, 4s orbital and 4p orbital is empty. MnCN63 minus cyanide has 12 electron. So D2sp3 hybridization will be formed. D2sp3 hybridization will show the octahedral geometry in an orbital complex because cyanide is strong field ligand but still unpaired electron is present, so it is paramagnetic. Then chromium CN63 minus ion. In this complex ion, oxidation state of chromium is +3 and valence shell electronic configuration is 3d3. Magnetic measurements show this complex ion is paramagnetic corresponding to the presence of 3 unpaired electrons. All the 3d electrons occupy just 3 of the 5 3d orbital, leaving two 3D orbital as vacant. This two vacant orbital combine with the vacant 4s and 4p orbital to give 6d2 sp3 hybrid orbital. These 6 hybrid orbital form bond with the ligand by accepting 6 electron pair of ligand. One pair from each of the 6 ligand. The 3 orbital of the metal cation have 3 unpaired electron and are degenerate. Thus, even in the presence of strong ligand, pairing of electron will not occur. If pairing of electron occur, then it will violate the Hund's rules of maximum multiplicity. Chromium atoms Z, atomic number 24, 3D, 4, 3D, 4 electron is present, 4s 1 electron is present. Chromium after losing 3 electron will form 3D will have 3 electrons and 4s 4p will be empty. Chromium Cn6 3 minus ion will share 12 electron will form D2sp3 hybridization. 3 unpaired electron is present, so this compound is paramagnetic. So D2sp3 hybridization octahedral geometry inner orbital complex. Here Cn6 3 minus show octahedral geometry inner orbital complex D2sp3 hybridizations. Fifth is vanadium NS363 plus ion. In this complex, ion oxidation state of vanadium is plus 3 and its valence shell electronic configuration is 3d2. Magnetic measurement indicates that this complex ion is paramagnetic corresponding to 2 unpaired electron. All the 2 3d electrons occupy just 2 of the 5 3d orbital, leaving 3 3d orbital vacant, 2 of which combined with vacant 4s and 4p orbital to give 6 D2sp3 hybrid orbital. The D2sp3 hybrid orbital form bonds with ligand accepting 6 pair of electrons, 1 pair from each of the 6 ligand. Out of 3 3D unhybridized orbital, the 2 orbital have 2 unpaired electron, 1 unpaired electron each, and 1 orbital remain vacant. These 3 unhybridized 3D orbitals are degenerate. Thus, even in the presence of strong ligand, pairing of electron will not occur. If pairing of electron occur, then it will violate Hund's rule of maximum multiplicity. Vanadium atom number 23, 3D 3, 4s 2, vanadium 3 plus ion. 4s will lose 2 electron, 3d will lose 1 electron. In 3D, 2 electron, 2 unpaired electron is there, 4s 4p will be empty. So VNS363 plus ions will share 12 electron. Then D2sp3 hybridization will form. D2sp3 hybridization show octahedral geometry inner orbital complex. Ammonia is strong field ligand. Various inner orbital octahedral complex are illustrated in 4.2. Table 4.2. Complex ion oxidation state of metal is plus 3. Valence shell configuration of metal cation 3d1. Nature of ligand. Water molecules weak field ligand. So um, in 3D, 1 unpaired electron is present. After giving 12 electron, we will get D2sp3 hybridization. So number of unpaired electron N is 1. VH263 plus oxidation state of metal will be plus 3. So valence shell configuration of metal cation will be 3d2. Nature of ligand H2 will be weak field ligand. So in vanadium 3d orbital, 2 unpaired electrons present. So H2 will give 12 electron and form D2sp3 hybridization. Number of unpaired electron N will be 2. CrH2O6 plus oxidation state of metal will be plus 3. Valence shell configurations of metal cation will be 3d3. Nature of ligand NS3 will be weak field ligand. So the 3d orbital will show 3 unpaired electron. H2O will give 12 electron. After sharing electron will form D2sp3 hybridization. Number of unpaired electron will be 3. Then chromium NH363 plus oxidation state of chromium will be plus 3. After losing 3 electron in chromium 3d orbital, 3 unpaired electron will be present. Ammonia is strong field ligands. So in 3d 3, so ammonia is strong field ligand. So 3d will have 3 unpaired electron. ammonia will share 12 electrons, will form D2sp3 hybridization. Number of unpaired electrons will be 3. Then chromium Cn6 4 minus, oxidation of chromium will be plus 2. So orbital of chromium will be 3d4. Cyanide is strong field ligand, so the 3d orbital of chromium will be 4. 4 will be there because cyanide is strong field ligand, so pairing of electron will be there. Cyanide will share 12 electron. It will form D2sp3 hybridization. 2 unpaired electron will be there. Manganese Cn6 4 minus, oxidation state of manganese is plus 2 and manganese 3d orbital will having 5 electron. Cyanide is strong field ligand, so 1 2 3 4 5, 5 electron will be there in 3d. So after sharing 12 electron, D2sp3 hybridization will form and number of unpaired electron will be 1. FeCN6 3 minus, so oxidation state will be plus 3. Fe will have 3d5 and Cn is strong field ligand, so the 3d will show 5 electron and will form D2sp3 hybridization. Unpaired electron will be 1. FeCN6 4 minus, oxidation state of iron will plus 2. Fe will have 3d6, Cn will have strong field ligand, so 6 electron will be present in 3d. Cyanide will give 12 electron, so it will form D2sp3 hybridization, so unpaired electron will be 0. So this is diamagnetic. FeCN5NO2 minus, so oxidation state of Fe will be plus 2. Fe will have 3d6. Cyanide Cn minus is strong, NO plus is also strong field ligand, so Cn and NO plus both are strong field ligand will form in 3d 6 paired electron will be there. Both Cn and NO is strong field ligand will give 12 electron and form D2sp3 hybridization, and it will be diamagnetic because a number of unpaired electron is 0. Then platinum Cl6 2 minus, oxidation state of platinum is plus 4. Platinum will have 5d6. Cl6 chlorine is weak field ligand, so platinum in the 5d orbital will show 6 electron and Cl6 6 chlorine will share 12 electron will form D2sp3 hybridization, so magnetic moment will be 0. Sorry, unpaired electron will be 0, that means diamagnetic. B. Outer orbital octahedral complex. In outer orbital complex, the central metal cation is sp3d2 hybridized. In sp3d2 hybridization, the orbital of outer shell, that is n-d orbital involved. Let us discuss complex by taking some examples. COFe 6 3 minus ion. In this complex ion, orbital state of cobalt is plus 3 and its valence shell electron configuration is 3d6. Magnetic moment measurements show that this complex is paramagnetic corresponding to 4 unpaired electron. Also, F minus is a weak ligand. There will be no pairing of 3d electron of the metal cation. Thus, there is no vacant 3d orbital, and none of the 3d orbital is available to accept electron pairs from the ligand. Consequently, the vacant 4s 4p and 2 of the 5 4d orbital combine to give 6 3 sp3d2 hybridization. This hybrid orbital form bond by accepting 6 pair of electron, 1 pair from each of the 6 ligand. So cobalt atom 3d will have several electron, 4s will have 2 electron, 4p and 4d will be empty. CO3 plus ion will lose 3 electron, and in 3d 6 electron will be present. 4s 4p 4d will be empty. So CFE 6 3 minus ions, where Fe will give 12 electron to form sp3d2 hybridization. sp3d2 hybridization octahedral geometry outer orbital complex. Second is FeH2O5NO2 plus ion. In this complex ion, oxidation state of Fe is +1 because NO exists in +1 oxidation state in complex of Fe, and its valence shell electronic configuration is 3d64s1. Magnetic moment measurement of this complex ion indicate that its experimental magnetic moment is 3.89 Bohr magneton, which correspond to 3 unpaired electron in the complex ion. The single NO plus strong ligand has little tendency to pair up the electron. It pair up only 2 unpaired electron. Since H2O is weak ligand, therefore it has no tendency to pair up the electron, and none of the 5 3d orbitals is vacant. Therefore the 4 is 4p and the 2 of the 5 4d orbital, that is 4dx2y and 4dz2 combined to give 6 sp3d2 hybrid orbital. This hybrid orbital form bond with 6 ligand by accepting 6 pair of electron, 1 pair from each of the 6 ligand. Iron atomic number is 26. 3d will have 6 electron, 4s will have 2 electron, 4p and 4d will be empty. So Fe plus ion. So in 3d 6 electron will be there and first 1 unpaired electron will be there. So FeNOH2O5 2 plus. NO is strong field ligand, H2O is weak field ligand. So both this weak field and strong field ligand will share 12 electron, will form sp3d2 hybridization. sp3d2 hybridization after the geometry outer orbital complex. Some outer orbital octahedral complex are illustrated in table 4.3. Table 4.3. Complex ions here H2O6 2 plus, oxidation state of metal is +2. Valence shells electronic configuration of metal ion will be 3d4. Nature of ligand is weak. H2 is weak field ligand, so valence bond electron description. So in chromium will show 4 unpaired electron 3d. So the H2 will share 12 electron to form sp3d2 hybridization. Number of unpaired electron will be 4. CrNH3 plus. Chromium will show +2 oxidation. Chromium will show 3d4. Ammonia is strong field ligand. So valence bond electronic descriptions. Chromium in its 3d orbital will show 4 unpaired electron. Then ammonia will give 12 electrons, so it will form sp3d2 hybridization. Number of unpaired electron will be 4. Then MnH2O6 2 plus, oxidation state of metal is +2. Then manganese will have 5 electron in 3d 3d5. H2O is weak field ligand, so in manganese 5 3d5 5 unpaired electron will be there. H2O will share 12 electron, will form sp3d2 hybridization. So number of unpaired electron will be 5. Then FeF6 3 minus or FeH2O6 3 plus will show +3 oxidations. 3d will show 5 electron, and Fe will and this Fe6 and H2 is weak field ligand. So in 3d 5 unpaired electron will be there, and sp3d2 hybridization will form. Number of unpaired electron will be 5. Then CO Fe6 3 minus, oxidation state of CO will be +3, and it will show 3d6. F will show, fluorine will show weak field ligand, so 3d will show 6 electron. Then F fluorine will show 12 electron, it will form sp3d2 hybridization. Number of unpaired electron is 4. Then CONH3 6 2 plus, cobalt will show +2, 3d 7, and ammonia strong field ligand, so 3d will show in cobalt 3d will show 7 electron. So ammonia is strong field ligand, so it will share 12 electron to form sp3d2 hybridization. Number of electron will be 3. nickel ammonia 362 plus. Nickel will be plus 2. Then nickel will show 3d8. Ammonia strong field ligand. So ammonia NH362 plus will show that nickel have 3d in 3d orbital 8 electrons present. Ammonia strong field ligand. It will give 12 electrons. It will form sp3d2 hybridization. Number of electron will be 2. From the foregoing discussion, it is concluded that octahedral complex of D1, D2, D3 metal cation are always in orbital complex. Whether the ligands are weak or strong, the octahedral complex of D8, D9 and D10 metal cation always out orbital complex. Either the ligands are strong or weak. The complex of D4, D5, D6 and D7 metal cation are orbital complex if the ligands are weak. Tetrahedral complex. In tetrahedral complex, the metal cation is either sp3 or sd3 hybridized. Let us consider some example to illustrate the hybridization in geometry. First, nickel Cl4 2- ion. In this complex ion, oxidation state of nickel is +2 and its valence shell electronic configuration is 3d8. Magnetic moment measurement indicate that it is paramagnetic corresponding to 2 unpaired electrons. Since Cl- is a weak field ligand, therefore no pairing of electron will occur in 3d orbital. None of the 5 3d orbital is vacant. Vacant 4s and 4p orbital combine to give 4 sp3 hybrid orbital because NiC nickel tetrachloride 2- is a tetrahedral complex ion. These 4 hybrid orbital form bonds with 4 ligands by sharing 4 pair of electrons, 1 pair from each of the 4 ligands. Nickel atom will show atom number 28, 3D will show 8 electron, 4s will show 2 electron and 4p. After losing 2 electron, nickel atom will change into nickel 2 plus ion. So in 3D, 8 electron will be present, 4s will be empty, 4p will be empty. So nickel Cl4 2- ions. So will form sp3 hybridizations by sharing 2 electrons by the Cl4 2-. It will form sp3 hybridization tetrahedral geometry. Nickel tetra carbon monoxide. In this complex, oxidation state of nickel is 0 and its valence shell electronic configuration is 3d8 4s2. Magnetic moment measurements indicate that nickel CO4 is diamagnetic, that is, it has no unpaired electron. Carbon monoxide is strong ligand and has the tendency to pair up the 3d electron. During the pairing of electrons, the 2 electron of 4s orbital shift into one of the 5 3d orbital. Thus 3 is no vacant 3d orbital. Thus the vacant orbital available for hybridization are 4s 4p to give 4 sp3 hybrid orbital. Nickel atom number is 28. 3d 8 electron, 4s 2 electron, 4p is empty. NiCO4 0 ion. So in 3d, so carbon monoxide will give 8 electrons. So it will form sp3 hybridization. sp3 hybridization tetrahedral complex. Third, MnO4- ion. In this complex ion oxidation state of manganese is +7. The valence shell electronic configuration of manganese is 3d5 4s2 and Mn7 plus ion. All 5 3d4s orbital vacant. The vacant 4s and 3d orbital combine to give 4 sd3 hybrid orbital. Thus Mn7 plus ion is sd3 hybridized in this complex ion as shown below. Manganese atom, atomic number 25, 3d is 5 electron, 4 is 2. After losing 7 electron, manganese atom will change into manganese plus ions. So 3d and 4s will be empty. Then MnO4- ion will share 8 electrons. So Sd3 hybridization will form. Sd3 hybridization tetrahedral complex will be formed. Then in Mn7 plus ion, energy of vacant 4s orbital becomes lower than that of vacant 3D orbital of the principal. In SG3 hybridization, vacant dxy, dyz, dxz orbital are involved. Cr2O72 minus ion in this complex ion oxidation state of chromium is +3 and its valence shell electronic configuration of chromium is 3d4 4s1. Chromium 36 plus ion has no electron in 3d orbital. The 4s and 3d or vacant orbit of each chromium 6 plus ion combine to give 4 Sd3 hybrid orbital. Thus each chromium 6 plus ion in Cr2O72 minus ion is Sd3 hybridized one of the 7 oxide ion share both chromium 6 plus ion. Cr2O72 minus ions SG3 hybridization. SG3 hybridization tetrageometry. It has no unpaired electron, therefore it is diamagnetic. Some tetrahedral complex are illustrated in table 4.4. Complex MnX4 to minus X such as halogen, chloride, bromide. Oxidation state is +2. Valence shells of manganese will be 3d5. So in manganese 3d, 5 unpaired electrons present. X4 will share 8 electrons. Number of unpaired electrons will be 5. And obviously halogens, whether it is bromide, chloride or fluoride, these all are weak field ligand. FeCl4 2 minus, oxidation state of Fe will be +2, valence shell will be 3d6, then Cl4 will share 8 electrons, then in 3d6 electrons are there, sp3 hybridization will form. Number of unpaired electron is 4. Cl4 2 minus, oxidation state of cobalt will be +2 and 3d7 valence shell will be there of cobalt. So in valence bond electrons, so in 3d7 electrons will be there. Then Cl4 will shares 8 electron will form sp3 hybridization. Number of unpaired electron will be 3. Copper X4 2 minus X will form Cl minus Br minus Cl minus. Oxidation state of cobalt, copper will be +2 and 3d will be 9. So X4 will share 8 electrons. sp3 hybridization will form. Number of unpaired electron is 1. Then copper Cn4 3 minus, oxidation state of copper will be +1, 3d will be 10. Cn will share 8 electron, sp3 hybridization will form. Number of unpaired electron is 0. Znx4 2 minus X will show Cl minus, Br minus, I minus. Oxidation state of zinc will be +2 and 3d 10 will be there in the valence shell. So in zinc 3d orbital will have 10 electrons. From halogen it will get 8 electron. sp hybridization will be formed. Number of unpaired electron is 0. Square planar complex. In square planar complex, the center metacation is dsp2 hybridized. The dsp2 hybrid orbital point towards the four corners of a square. Let us consider some example to discuss the hybridization in square planar complex. First, nickel Cl4 2 minus ion. In this complex ion, oxidation state of nickel is +2 and its valence shell electronic configuration is 3d8. Magnetic moment measurement indicate that this complex ion is diamagnetic, that is, it has no unpaired electron. Since Cn minus is a strong ligand, therefore this ligand causes to pair up the two unpaired electron in 1d orbital, resulting in vacant 3d orbital. This vacant 3d orbital get hybridized with the vacant 4s and 2 of the 4p orbital to give 4 dsp2 hybrid orbitals. This hybrid orbital form bonds to the ligand by accepting 4 pairs of ligand electron, 1 pair from each of the 4 ligand. Nickel atoms, atomic number is 28, 3d 8 electron present, 4s 2 electrons present, 4p is empty. Then after losing 2 electrons it will change into nickel 2 plus. In 3d 8 electron will be there, 4s 4p will be empty. NiCN4 2 minus ion will share 8 electron, will form D2 dsp2 hybridization. dsp2 hybridization will form square planar geometry copper Ns342 plus ion. In this ion, oxidation state of copper is +2 and its valence electronic configuration is 3d9. Magnetic moment measurement indicate that this complex is paramagnetic, corresponding to presence of one unpaired electron. There is no possibility of pairing of electron by the ligand. Even the ligand is strong because there is only one unpaired electron in 3d orbital. Since coordination number of copper is 2 plus ion in copper Ns342 plus is 4. Therefore, according to VBT, copper 2 plus ion should be sp3 hybridized and the structure is tetrahedral. Copper atom atomic number is 29. 3D will have 9 electrons, 4s will have 1 electron, 4p will be empty. Copper 2 plus after losing 2 electrons. In 3D, 8 electron will be 9 electron will be present, and in 4s and 4p will be empty. CO copper Ns342 plus ion will share 8 electron to form sp3 hybridization. sp3 hybridization tetrahedral geometry. But according to ESR and X-ray structure determination, the structure of copper Ns342 plus is found to be square planar. Thus, to make copper 2 plus ion in ds2 hybridized, it is considered that unpaired electron in 3dx2 y2 orbital is to be promoted to 4pz orbital as shown below. Copper Ns342 plus ion will form ds2 hybridization. ds2 hybridization square planar geometry. In the above electronic configuration, the unpaired electron is present in the higher energy 4pz orbital and is expected to be lost easily, that is, copper Ns342 plus ion may be easily oxidized to copper Ns343 plus. Copper Ns32 plus oxidation of copper Ns343 plus electron, but experiment has shown that copper Ns343 plus ion does not exist, that is, oxidation of copper Ns342 plus to copper Ns343 plus is not possible. Finally, Huggins suggested that in square planar copper Ns342 plus ion, copper 2 plus ion is sp2d hybridization as shown below. Copper Ns342 plus ion will show 9 plus 8 will be 17 electron. One unpaired electron is present, it will form sp2d hybridization. sp2d hybridization square planar geometry. In this configuration, one of the 3 4p orbital 4pz orbital remain unhybridized, that is, does not participate in hybridization because pz orbital lies above and below the plane of the ion. Copper py2 2 plus copper En2 2 plus copper Cn4 2 minus complex ion are square planar and copper 2 plus ion is sp2d hybridized. The valence bond electron description of some square planar complex is given table 4.5. Complex NiHg DMg2. Oxidation of state of nickel is +2. Valence shell electronic configuration of nickel is 3d8. So T2sp dsp2 hybridization will form after sharing 8 electron. Number of unpaired electron is 0. Copper Cn4 2 minus. Oxidation state of copper is +2. Valence shell of copper is 3d9. After losing 2 electron, it will form sp2 dehybridizations. After cyanide shares 8 electron, number of unpaired electron will be 1. Then PdCl4 2 minus. Oxidation state of palladium is +2. Large valence shell of palladium is 348. So palladium tetrachloride 2 minus will form dsp2 hybridization after sharing 8 electron by ligand. Unpaired electron will be 0. Then platinum tetrachloride 2 minus. Oxidation state of platinum will be +2. Large shell of platinum will be 5d8. So it will form dsp2 hybridizations when it will get 8 electrons. Unpaired electron will be 0. Then platinum Ns342 plus. Oxidation state of platinum will be +2. Then a large shell of platinum will be 5d8. So it will form dsp2 hybridization after getting 8 electron, and oxidation and number of unpaired electron will be 0. So limitation of VBT, valence bond theory. First, it could not explain the nature of ligand, that is which ligand is strong and which one is weak. Second, it could not explain why the pairing of electron occur in the presence of strong ligand. Third, from this theory, magnetic moment can be calculated by knowing the number of unpaired electrons, but it could not explain the effect of temperature on magnetic moment. It could also not explain why the experimental value of magnetic moment is greater than the calculated in some complexes. Fourth, it could not explain the distortion in some octahedral complex like CrH2O6 2+ and COH2O6 2+. Fifth, it could not explain the color and electronic spectra of complex. Sixth, it could not explain the reaction rates and mechanism of reaction of complex. 7. It could not explain the structure of copper NH3 4 2+ ion.